Section 16 is entitled Area and Arc Lengths in Polar Coordinates. First problem we want to do is to find the area of one petal of r is equal to 2 cosine 3 theta. So the first thing we should do is find one petal. Let's find out when cosine of 3 theta is, say, equal to 1. Well, cosine is 1 at 0. So 3 theta can be 0. So theta is 0. What that tells me is that one petal is around 0. And then I know that r value is 2 times 1, or 2. Not that that mattered. Now, I'm just going to find the area of the top half. Why? Because I know the lower angle. The lower angle is 0. I just need to find this angle, as opposed to finding that angle and that one. I'm just going to find one of those angles. So in terms of my integral, it's going to be 2 times their formula for their area, which is 1/2 times r squared d theta. R squared d theta. But of course I need to plug in my limits. I need to plug in the limits. Remember, I'm only finding the area of the top half, and that's why I'm doubling it. In fact, the doubling cancels out, but that doesn't mean I'm not doubling. I know the lower one is 0. I need to find the upper one. Well, I know one thing about this point right here. It's where r is 0. Right here, r is 0. It's a coincidence that r is 0. So I said 2 cosine 3 theta equal to 0. And it's probably 0 in a lot of places. For example, if I have many of these petals, it's 0 many times. It's 0 coming in from here, going in from there, coming in this way, coming in that way, coming in this way, that way. It's 0 many times. Well, I want to know the smallest time it's 0, because that's where the first petal is. Well, if 2 times that is 0, it must be that's 0. And cosine is 0. The smallest time cosine is 0 is at pi over 2. So I let 3 theta equal pi over 2 divided by 3. I get pi over 6. That's when I'm going to integrate from 0 to pi over 6. Integrate from 0 to pi over 6. Okay, so let's get rid of some of this, and let's do the integration. First I have to square. So it's the integral from 0 to pi over 6, and I square this. 2 squared is 4. I'll put that in front. Cosine 3 theta squared is cosine squared 3 theta times d theta. Now we have a rule or a theorem that says cosine squared of u, cosine of 0 is 1. So it's 1 plus cosine of twice u over 2. Whatever the angle is, it gets doubled. Okay? So it's 1 plus this here is 1 plus cosine of twice that, 6 theta over 2 d theta. Okay, you have to know the half angle formula, or maybe the double angle formula. It's a formula. Doesn't matter what we call it, you have to know it. And again, we integrate from 0 to pi over 6. Coincidentally, 2 goes into the 4 2 times. We have 2. The integral of 1 is theta. The integral of cosine 6 theta is plus the sine of 6 theta over 6. From 0 to pi over 6. So first we plug in pi over 6. And factoring at that 2 big times. So you get pi over 6 plus something over 6. Well, 6 times theta, 6 times pi over 6 is pi. So you get the sine of pi. Minus, now plug in 0 for theta. Theta is 0 plus 6 times 0 is 0 over 6. Let me come to the left here, please. The 2's factored out. Pi over 6. The sine of pi is 0. 0 over 6 is 0. And the sine of 0 is 0. 0 over 6 is 0. And of course 0 is 0. So I just get 2 times pi over 6, which is pi over 3. 2 goes into 6 3 times. Pi over 3 is the answer. The area of this one petal, this one entire petal, is pi over 3. Just do half of it. It's a lot easier plugging in 0. It's a lot easier plugging in 0. Look, I got 0. I got 0. You plug in the other angle, which I bet is negative pi over 6. In fact, I'm sure it is due to symmetry. This angle is going to be negative pi over 6, this angle here. But then it's just not going to be that friendly. Okay, let's try another similar problem. Suppose we want to find the area of the interior of R is equal to 1 minus sine theta. Okay, what you need to know about sine theta is that you have symmetry from left to right. If you have this to the left, then you're going to have the same thing to the right. If the left goes like that, if the right goes like that, excuse me, the left goes like that. If the left goes like this, if the right goes like this, then the left goes like that. It's a mirror image. So, if you think about it, if the angles go in between there, it's going from 3 pi over 2 to pi over 2. Or if you preferred, negative pi over 2 to pi over 2. So that's what we do. So we're going to find the area of the left, of the right. We're going to find the area of the right half. So it's going to be the integral from negative pi over 2 to pi over 2 of r squared d theta. But that's just the right half. We want the left half as well. So we double our answer. Because of symmetry, whatever is the right half, and have the same area in the left half. If I told you that this area was 9 square inches, well then that's going to be 9 squared inches. If this area was 3 pi over 2, that area will be 3 pi over 2. It is just double it, and you get the whole thing for free. For cosine, the top and the bottom are the same. That is, what you have up there, you're going to have the same graph down there. So you can just go from 0 to 180 with 0 to pi. Okay, coincidentally, 2 times the half, forget about it, gives 1. So we have the integral from negative pi over 2 to pi over 2 of this squared d theta. 1 minus 2 sine theta plus sine squared theta. But we don't know how to integrate sine squared theta, but that's 1 minus cosine 2 theta all over 2 d theta. What I will say is 1 plus 1 over 2, I can combine that. It's just 3 over 2. It's 3 over 2. And the integral of 3 over 2 is 3 theta over 2. Minus 2 times the integral of sine theta is negative cosine theta. Minus, there's my over 2. That over 2. The integral of cosine of 2 theta is sine of 2 theta over 2. Which means over 4. And this gets evaluated from negative pi over 2 to positive pi over 2. So first I plug in pi over 2. I get 3 times pi over 2 times the 2 that's in the bottom. And I get 4. 2 times 2 is 4. If you divide by 2 and then you divide by 2 again, you divide it by 4. You have this 3 pi over 2. That means this 3 pi is getting divided by 2, and then you divide it by 2 again. 2 times 2 is 4. Plus 2 times cosine pi over 2 minus the sine of 2 times pi over 2, which is pi, over 4. Minus, now I plug in negative pi over 2. So I get negative 3 pi over 4 plus 2 times. Now, the cosine of a negative angle is just the cosine of the angle. I just get 2 cosine pi over 2. I have positive 2 cosine over 2, and I have positive 2 cosine over 2 over here, and I'm subtracting them. You better believe I'm just going to cross them out. Minus the sine of 2 times negative pi over 2, which is negative pi. When it comes to our signs, the negative you can bring in front. It becomes plus. And this is over 4. Okay, let me erase some of this and continue. Well, you have 3 pi over 4, and you're taking away negative 3 pi over 4. You have 6 pi over 4. You end up adding them. And the sine of pi is 0. The sine of pi is 0. Over 4 is still 0. So there's the answer. 3 pi over 2. Okay, 3 pi over 2. Integrate from negative pi over 2 to pi over 2. Now you might want to graph that to make sure that it really required you to go from negative pi over 2 to pi over 2. The right half will definitely look like the left half, but in some graphs it's possible to go from here to there where the angle only went between 0 and pi over 4. Okay, so you would integrate from 0 to pi over 4, and since it's a sine graph, you know that the other half, the left half, is the same, so you happen to have a half in that integral. R theta squared d theta and then you double it. I'm sure that in that last graph, it went from negative pi over 2 to positive pi over 2. Graph it. Make sure that's what you needed. Okay, the next one, it asks us to find the points of intersection. We want to find the points of intersection, if any, of these two graphs. Now, let's just suppose for a moment that the first graph contains 0, pi. That means r is 0, and the angle is pi. And the second graph contains 0, pi over 4. Well, those points are equal. They don't look equal, but they're equal. Because here is pi. Here is pi. I go along there 0. That is, I'm right at the origin. And here is pi over 4. And I go out 0. It's the same. Okay? These points are equal. So if both graphs allow r to equal 0, for argument's sake, we'll always call it 0, 0. 0, any angle, we'll call it 0, 0. So if the r's can both be 0, then you have a point of intersection. Now, setting the two r's equal to one another doesn't always catch that one. We have to check to see if both r's can equal 0. But to find the other places where they're equal, we set the r's equal. We used to set the y's equal to one another. Now we set their r's equal to one another. I take away 1 from both sides. Add cosine theta to both sides. You get 2 cosine theta is 0. That means cosine theta must be 0. So theta can be pi over 2 or 3 pi over 2. Pi over 2 or 3 pi over 2. And now we want the corresponding r values for pi over 2. R of pi over 2, well, that's 1 plus cosine pi over 2. And the cosine of pi over 2 is 0. So we get 1. So there's 1 point. 1 comma pi over 2. R comma theta. Now, R 3 pi over 2. Now it doesn't matter which curve you look at, the top one or the bottom one, because at pi over 2 they're supposed to be equal. I mean, we can check the other one. This is 1 minus the cosine of pi over 2. But pi over 2 is 0, and 1 minus 0 is 1. So when theta is pi over 2, both r's are 1. So it does work like a charm. Now, what about 3 pi over 2? Pick any one of them. R of 3 pi over 2. I'll choose the top one. I get 1 plus cosine 3 pi over 2. Well, 3 pi over 2 is 0. So again, I get 1. R is equal to 1. But now we have to check this isolated case. Can the r's both equal 0? They both have to equal 0. Can the r's equal 0? Can 1 plus cosine theta equal 0? That is, can this be negative 1? Of course. Okay, it's negative 1 at pi. So the first graph has the point R comma theta, 0 pi. In the second graph, it too can equal 0 when this is 1. And cosine of theta is equal to 1 when theta is 0. So we have that r is 0 and theta is 0. As long as r can be 0 in both of the graphs, they're both going to have that point in the origin. I don't care what they call an angle. 0 pi is the same as 0 pi over 2. In particular, it's the same as 0, 0. But like I said, we'll always call it 0, 0. So the 3 points, which I'll put up here, are 1 pi over 2, r comma theta. The other point is 1 comma 3 pi over 2. It's called a coincidence that they're both 1s for r. And the last one is 0, 0. These are the 3 points of intersection of these two graphs. In addition to setting them equal, in addition to setting the two r's equal, you must check to see if the r's separately. You must check to see if the two r's can both be 0. If one of them can be 0, but not the other one, well, they won't have the origin in common. Suppose you have same problem. Find the points of intersection. Suppose you have that r, the other r is 1 minus sine theta. The first thing you do is you set them equal to one another. The next thing I would do is I would take away 1. Cosine theta is equal to negative sine theta. That might be hard for some of you. Not a big deal. Divide both sides by cosine theta. Why cosine theta? Because I know what sine theta over theta is. It's a friendly one. It's tangent. The left side is 1. Well, that must be negative 1. 1 is equal to negative 1. Or, here's a smooth thing, if two quantities are equal. Negative 7 is equal to negative 7. If I change both signs, they're equal. If you come to know that negative x is negative 2, you can change both signs and say x is 2. If you know negative x is 5, you can change this sign and change that sign. Change, change. Tangent of theta is negative 1. Well, there's two places where tangent of theta is negative 1. In quadrant 2, and quadrant 4. And both of the reference angles are pi over 4. So this angle would be 3 pi over 4. And this one would be not quite 8 pi over 4, which is 2 pi, for 1 less. 7 pi over 4. So theta can be 3 pi over 4, and theta can be 7 pi over 4. Now we just have to go and find their r values. Now, you don't need to check it in both r's. You don't need to plug in 3 pi over 4 into both r's unless you want to check it, which is fine. R is equal to 1 plus cosine 3 pi over 4. Well, cosine of 3 pi over 4, well, the angle's right here. That angle is 3 pi over 4, which makes that pi over 4. So it's 1 square root of 2. This is negative. This is positive. The cosine is negative 1 over square root of 2. Minus 1 over square root of 2. Which is 1 minus square root of 2 over 2. Think of the 1 as 2 over 2. Over 2. So it's 2 take away square root of 2 over the common denominator. R is 2 minus square root of 2 over the common denominator. Now, it turns out that the cosine of 7 pi over 4, that puts me in quadrant 4, this reference angle is also pi over 4. 1 square root of 2, positive, negative. The cosine is positive 1 over square root of 2. So it just becomes plus. Just becomes plus. 2 plus square root of 2 over 2. Those are 2 points. R theta, R comma theta. Now, like always, we have to see if these r's can equal 0. Now remember, sine theta can equal any number between plus and minus 1. Cosine theta can equal any number between plus and minus 1. So we don't have to really find the angle r equals 1 plus cosine theta. Bring the 1 over, you get negative 1 cosine theta. Okay, that's okay. And the angle is pi, but we know it's going to exist. That is, r can equal 0. For example, if you had r is equal to 2 plus cosine theta, this would have to be negative 2, but that can't be. That can't be. Cosine theta is between negative 1 and positive 1. When you want to write down the answer, theta can be pi. So that tells me r is 0 and theta is pi. 0 pi. For the second one, 1 minus sine theta. Can this be 0? If that can be 1. 1 minus 1 is 0. And sine theta can be 1. Sine theta can be 1. At pi over 2, for example. So that tells me r is 0 when theta is pi over 2. That tells me we have 0, 0. These are the 3 points of intersection. 0, 0. 2 plus square root of 2 over 2, comma, 7 pi over 4. This r down here, comma, 3 pi over 4. R comma theta. If it's an exam and you want to get full credit, you really need to write it down in parentheses with a comma in the middle, r to the left, theta to the right. 2 minus square root of 2 over 2, comma, 3 pi over 4. That's 1 point of intersection. The second point will be, or a second point is this, 7 pi over 4. And the third point is 0, anything. Or we're going to say 0, 0. And those are the 3 points of intersection. Always check to see if the 2 defined points of intersection, in addition to whatever else you do, namely setting the r's equal to one another, you have to check to see if the r's can both equal 0. Now here's an interesting one. Suppose you have r is equal to theta over 2 and r is equal to 2. Now, r equals 2 gives you that. R is always 2. But you know what? This is the same as r is equal to negative For example, let's just make up a table. Theta, r. If theta is 0, r is negative 2. R is always negative 2. If theta is pi over 2, r is negative 2. If theta is pi, r is negative 2. If theta is 3 pi over 2, negative 2. If it's 7 pi over 15, negative 2. Now, we have this rule that r comma theta. If you add, so you have this point right here, r comma theta. That is, this distance is r, and the angle is theta. Well, let's consider this angle. Wouldn't that angle be theta plus pi? Now, if I told you, go out to theta plus pi, that is out here. And I say the r value is negative r. That means instead of going to r, you go backwards. You end up right here anyways. You end up right here. These two are equal. Okay, so that means I can add pi. Well, first it's r comma theta. If I change the sign of r, then I can add pi to the angle. If I change the sign of r, I can add pi to the angle. I can change the sign of r, and I can add pi to the angle, or take away pi. I can change r and add or take away pi. I can change the r, sign of the r, and add pi. That is, add 30 pi over 2. Okay, 30 pi over 15. And I get 37 pi over 15. But these are just any angle. R is always 2. Okay, that's the same as that. You have to be slick to see that one. I mean, some problems you're not going to get right. Okay, and this is one of them. This is a sneaky little problem. Okay, so I set the r as equal. But in the second equation, r can really be plus or minus 2. If r is 2, then its r can be negative 2. So we have theta over 2 is equal to plus or minus 2. Multiply both sides by 2, theta can be plus or minus 4. Okay. Now I know what r is. Oh, maybe I don't. R is plus or minus 2. Well, let's use the top one. When theta is negative 4, that implies r is negative 4 over 2, which is negative 2, which means r theta. And when theta is 4, that implies r is theta over 2, which is 2. So we know what r is, we know what theta is. These are 2 points of intersection. Now, can we ever have r equaling to 0 for both of them? The answer is no. If r is 2, it's not 0. If r is negative 2, it's not 0. The second one, the circle. The circle. Let's face it, it doesn't cross the center. Of course, in the top one, if theta is 0, you get 0 over 2, which equals 0. I may not know what the second one looks like, but I know one thing. It crosses 0, 0. It might be that. It crosses 0, 0. But the other graph does not. R equals 2 or negative 2. It doesn't cross. Okay, so possibly a lot of people may say, oh, the answer is only 2, 4. Nope. Negative 2, negative 4 also works. Which, okay. You get the same points on r equals negative 2 as you do on r equals 2. Now you want to find the area in common between two curves. And we want to find the area in common between two curves. Suppose you were given that r is equal to 4 sine 2 theta and r is equal to 2. Now let's graph this. The second graph, the bottom one, r equals 4 sine 2 theta, looks like one of these multi-leaf roses. So we take the sine of 2 theta, we set it equal to the magic number 0. Excuse me, 1. And negative 1. Well, the sine is 1 at pi over 2. 2 theta is pi over 2. Now, let me just argue why we just want to find one petal. Suppose it has many petals. And they all really should be the same size. And the height of the petal is 4. So 2 is less. Well, I want to find the area between these two graphs. That is, I want this area and this area. Okay, it turns out, let me just draw less of these. And here's 2. Turns out that this area is going to be the same as this area, which is going to be the same as that area. Okay, so I need to know how many of these petals we're going to have, and I just want to find one of the intersections. I just say want to find out that area, and given the picture I have, I'll multiply it by 3. But better yet, possibly, I'll just find the upper half. I'll just find the upper half, and then I'll multiply it by 6, because there's 6 of those. So, we need to understand our graph a little bit better. We need to know how many petals we're going to have. If you do enough of these, you realize that it's going to be twice the number in front of theta. Okay, 2 pi over, now you can add 2 pi. That is, you can add 4 pi over 2. 4 pi over 2 is 2 pi. So you get 5 pi over 2, 9 pi over 2. Divide by 4. Excuse me, divide by 2. So theta is pi over 4, 5 pi over 4, and then 9 pi over 4. The 9 over 4 is more than 2. I don't want more than 2. Cosine of sine of theta is negative 1 at 3 pi over 2. 3 pi over 2. Then you add 2 pi to it. 7 pi over 2. Divide by 2, you get 3 pi over 4. 7 pi over 4. Okay, so we have a lot of pi over 4s, so let's do that. So at pi over 4, you go out to 4. You go out here. And at 5 pi over 4, you go out to 4. At 3 pi over 4, which is along here, you go negative 4, which brings you here. And 7 pi over 4, believe it or not, is along this one. But you have to go back negative 4, which brings you there. So we get 4 petals. We get that graph. 2 times that number. We get 4 petals. At the pi over 4s. Try to erase this again. Okay. There are my perfectly drawn 4 petals. And r equals 2 is like that. So like I said, why don't we just find out one of those areas? Why don't we just find out one of those areas? Then I'll multiply it by 8. Okay, so it's going to be 8 times some integral. Now, what I want to do is, I want to draw this a lot bigger. There's the lower half of the petal, and here is 2. R equals 2. So this point of intersection is very important, because when I go out to that angle, this area is just the area in the petal between the 2 angles, between 0 and whatever angle is right here. Now, above that, that is, for this angle in here, we just go out to 2. Doesn't even care about the petal anymore. Doesn't even care about the petal. So we need to find the points of intersection. And we want the first one above 0. We want the smallest one. We need to find out the points of intersection. I want to know when one R is equal to the other R. Divide both sides by 4. You get 1/2 is equal to the sine of 2 theta. Well, when is the sine of an angle a half? The answer is at 30 degrees. 1, 2, square root of 3. 30 degrees, pi over 6. So 2 theta must be pi over 6. So theta is pi over 12. This angle up here, this angle right here is pi over 12. Now I've already calculated, I just remembered that that angle is pi over 4. So I'm going to find the area inside the petal, between the petal and the circle, on just half of the petal. That is why I'm multiplying by 8. And my 8 is already there. My 8 is already out there. So first I'm going to find, or try to calculate, the area of this little piece here. It's 1/2 integral from 0 to pi over 12, and it's the leaf. It's the 4 sine 2 theta graph. 4 sine 2 theta squared d theta plus this area in here. Well, that's It's 1/2 the integral from pi over 12 to pi over 4 of the radius squared, of r squared. But r is just 2. 2 squared is 4, d theta. And there it is. Now it's just calculus. Step 2, integrating. Just integrating. Okay, let me get rid of this picture, and I'll comment that I can factor out the 1/2. And when I factor out the 1/2, half times 8 is just 4. So it's 4 times the integral from 0 to pi over 12 of this, which is 16 sine squared 2 theta, d theta, plus the integral from pi over 12 to pi over 4. The 4 I'll put in front, so I just have d theta. Okay, so I have 4 times the first integral. The 16 I can pull out in front. The sine squared of 2 theta, sine is 0. So it's 1 minus the cosine of double that angle divided by 2. I'll put the 2 in front. D theta. And of course 16 over 2 is 8. Plus 4, the integral, well, let me not do the integral yet. I'll do both integrals at the same time. So I get 14 times 8 times this integral. The integral of 1 is theta, minus the integral of cosine 4 theta is sine 4 theta divided by 4. And this goes between 0, but it's evaluated between 0 and pi over 12. Plus 4, the integral of d theta is theta. And this goes from pi over 12 to pi over 4. Okay, now, so long as I don't mess up the evaluation, I think I have this going correctly, which is a miracle. So I have 14 in front of everything, and then I plug in pi over 12 for theta. So I get 8 times pi over 12 minus the sine of 4 times pi over 12. And 4 goes into 12 3 times. So I get pi over 3. And this all gets divided by 4. And then you plug in 0. You plug 0 and you'll get 0. And 4 times 0 is 0. And the sine is 0 is 0. Over 4 is 0. 0 minus 0 is just 0. Okay, plus 4 theta. First I plug this in. I get 4 times pi over 4, which of course is pi, minus 4 times pi over 12, which is pi over 3. Close the big brackets. So let's see what we have here. Okay, so we have 14 times 8 times pi over 12 minus pi over 3 is 60 degrees. And the sine of 60 degrees, 1, 2, square root of 3. The sine of 60 degrees is square root of 3 over 2. So you have square root of 3 and you divide it by 2. But then you divide it by 4. That is, you divide it by 8. Plus, this is pi minus pi over 3. So we just need to clean this up. It needs a lot of cleaning up. times everything. Well, 8 times this. 8 times pi over 12. 4 goes in here 2 times. 4 goes in here 3 times. You get 2 pi over 3. Okay? 2 pi over 3. Minus 8 times that. The 8's will cancel. You just get square root of 3. Plus pi minus pi over 3. Okay, let us try to combine stuff. Let us try to combine stuff. Now, it's just silly algebra. 2 pi over 3 plus negative pi over 3. 2 pi over 3 plus negative pi over 3. You can always change those two signs. So it's 2 pi over 3 minus pi over 3. The denominators are the same. Keep it. 2 pi's minus 1 pi is pi. So this plus this is just pi over 3. Plus another pi minus the square root of 3. Okay. I can think of this addition of pi as 3 pi over 3. So now I have 14 times 4 pi over 3 minus the square root of 3. But I'm going to multiply top and bottom by 3. That way I have a common denominator. And I factor out the 3 on the bottom, and I get 4 pi's minus 3 square root of 3's. And that finishes up that problem. You have to see where they intersect, because sometimes you have to integrate over one curve, and other times you have to integrate over another curve. Okay. Suppose you have this. This one is quite interesting. Find the area of the common interior. R is equal to 3 minus 2 sine theta. And the other R is negative 3 plus 2 sine theta. Now, if you notice, this is negative 3 minus 2 sine theta. That is, it's negative that. If I call this R2 and that R1, then this is negative, and that's R2. That is, R1 and R2 just differ by a sign. Okay, so if things differ by a sign, if I tell you that x is equal to negative x, that means x is 0. You can add x to both sides, and you get 2x is 0, and yes, x is 0. So you may say, well, I take my R, and I want to know when they equal 0. Well, if you subtract two things and you get 0, then the two things are immediately equal to one another. Divide by 2, divide by 2. On the right side, you get sine theta. On the left side, you get more than 1. No solution there. So you may say, well, these things don't intersect. But you have to be careful. You have to be a little bit careful. They might still intersect. If the angles differ by theta, then the r's will differ by a sign. Remember that r comma theta is equal to negative r comma theta plus pi. Those are equal to one another. So let's just try 0 and pi. Now, if you were to graph this, the top one, when theta is 0, and theta is pi over 2. Okay. The top one, if you just graph the right half, it'll look like that. The bottom one is going to be exactly the same, except it just goes the other way. Just goes the other way. They're going to cross at 0. If you look at R and, let me draw the other half of the top graph. And let me draw the other half of the bottom graph. Okay, they don't look the same, but trust me, they are. They're intersecting here. Now, if you take R2 of 0, you get 3 minus 2 sine of 0. Sine of 0 is 0, so you get 3. That is, you get R comma theta. That's from R2. Now, if you do R1 of, say, pi, you get negative 3 plus 2 times the sine of pi. But the sine of pi is 0. So you get negative 3 plus 0, or twice 0, is 0. That is, R is negative 3, the angle is pi. Same point. They're the same point. To do negative 3 pi, you go out to pi. Here's pi. But this is also pi. The whole line is pi. When you're talking about pi, here's positive 1, positive 2, positive 3, positive 4, negative 1, negative 2, negative 3, negative 4. There it is. That's negative 3 pi. Now, if you're just talking about, 3, 0, here is the angle 0. In fact, 0 goes in that direction. That's the positive direction. Here is positive 1, positive 2, positive 3. That's 3, 0. This would be negative 1, negative 2, negative 3. What do you know? Those are the same points. They actually intersect there. Okay. So now that we found out where they intersect, and that it's the sine graph, that means you have left and right symmetry. And in this graph, since one R is a negative of the other, you actually have top to bottom symmetry in this case. That is, this area here is exactly the same as this area, which is exactly the same as this area, which is exactly the same as this area. So what I'm going to do is I'm just going to find the area of any one of them and multiply it by 4. Multiply it by 4. So it's the integral of 1 is 1/2 the integral of r squared d theta. Now, let me just do this one. This angle goes from 0 to pi over 2. So I do 3 minus 2 sine theta squared from 0 to pi over 2. And half for 4 is 2. So I get 2 times the integral of, from 0 to pi over 2 of 9 minus 12 sine theta plus 4 sine squared theta. The sine squared theta is 1 minus cosine 2 theta over 2. And the over 2, 4 over 2 is just 2. Okay, let's get rid of the picture and let's start doing some calculus and integration. D theta. Let's distribute that too. 9 minus 12 sine theta. Positive 2 times 1 is positive 2. You add that to the 9, you get 11. Positive 2 times negative cosine 2 theta is negative 2 cosine 2 theta. D theta. Now I integrate. The integral of 11 is 11 theta minus 12. The integral of sine theta is negative cosine theta minus 2 times. The integral of cosine 2 theta is sine 2 theta over 2. Coincidentally, the 2's cancel. And we're evaluating from 0 to pi over 2. And we go way to the top. And we plug in. First we plug in pi over 2. We got 2 in front, stays. So we get 11 pi over 2 plus 12 times cosine pi over 2 minus the sine of twice pi over 2, which is just pi. Minus, and now we plug in 0. We get 11 times 0 plus 12 cosine of 0 minus the sine of twice 0, which is 0. Two. 11 pi over 2. Now, the cosine of pi over 2 is 0. The sine of pi is 0. The sine of 0 is 0. 11 times 0 is 0. Okay, the only thing that survived is, well, we have a minus 12 times 1. Cosine of 0 is 1. 12 times 1 is 12. So you get 2 times that. The 2's cancel. You get 11 pi's minus 2 times 12, 24. There's the answer. You need to do a lot of these, and you need to have some good examples to work from. Hopefully I'm giving you that. Okay. Like this section was entitled Area and Arc Lengths and Polar Coordinates. How about we do some arc lengths problems? Turns out that the arc lengths and polar coordinates, S for arc lengths, well, it equals angle angle alpha to angle beta of alpha theta squared plus f prime or theta squared. Now remember, f for theta is r, and f prime of theta is r prime squared d theta, and we must take the square root of this. So, suppose I tell you that r is just a, and that theta is in between, that's the symbol for theta, is in between 0 and 2 pi. That's alpha, that's good old beta. And I'll assume a is positive. So S is equal to the integral from 0 to 2 pi of the square root of r squared. That's r squared plus. Now, the derivative of r, if r is a constant, the derivative is 0. 0 squared. D theta. Well, this mess is just a squared. And the square root of a squared is 8. So I just get 8. I just have a d theta from 0 to 2 pi. A is a constant. Put it in front. The integral of d theta is theta from 0 to 2 pi. I'll even factor out the 8. 2 pi minus 0. Why, that's 2 pi. And generally you write the answer as 2 pi 8. That's the arc length, if r is just equal to 8. Now, does that make sense? I mean, maybe this is absurd. If r is 8, that means, that distance is 8. That distance is 8. That distance is 8. The arc length, that's a circle. The arc length is 2 pi times the radius. The radius is 8. That's just what we got. That's just what we got. Okay, so we now know how to derive the formula for, we knew this earlier from Calc 1, but now we learned a new way of deriving the formula for the circumference of the circle. Here it is. R equals A. Find the arc from 0 to 2 pi. The whole circle, 0 to 2 pi. Bingo, we got 2 pi 8. It's good to know what the answer should be, especially on an exam. That way, if you don't get the right answer, well, I mean, do what it takes to get the right answer. Do something different. Suppose you know that r is equal to 2 theta, and this time you want to go from 0 to pi over 2. You want to find the arc length. Well, the arc length is the integral from alpha to beta from 0 to pi over 2 of the square root of r squared, 2 theta squared, plus the derivative, which is 2 squared, d theta. So this gives us the integral of the square root of 4 theta squared plus 4 d theta. I can factor out a 4. I get 4 times theta squared plus 4 d theta. But if you have a product underneath the square root sign, you can take the product of the square roots. That is, you could have 2 square roots. And I happen to know the square root of 4. I'll bring it in front. Even if I didn't know the square root of 4, I would bring the square root of 4 in front. And I do have a typo. That should be a 1. 4 times 1 is 4. Okay, so this is 2 times the integral of the square root of theta squared plus 1 d theta. This last integral, that's done by trig substitution. It's a classic trig substitution integral. 2 times the integral of the square root of theta squared plus 1 d theta. Well, I introduce u, make a u substitution. I call that side theta squared plus 1. I'll call that theta and that 1. The Pythagorean theorem is justified. Theta squared plus 1 squared, which is 1. It does equal to the hypotenuse squared, which is theta squared plus 1. Okay, Pythagorean theorem is valid here. And it better be, it's a right triangle. If it weren't correct, then the sides are labeled wrong. Well, in this case, the tangent of u gives me theta over 1, which is theta. Now, I'm glad I got theta, because I need to get d theta. we take the differential of both sides. Secant squared u du is equal to d theta. So I have another way of writing d theta using just u's. I just now need another way of writing theta squared plus 1 square root. Well, the secant of u is hypotenuse divided by the adjacent. It's exactly what I wanted. Theta squared plus 1 divided by 1. Dividing by 1, the rule is don't bother doing it. Okay, so what we get is 2 times the integral from 0 to pi over 2 it was. This piece is secant of u. Secant of u times this piece, says it right here, it's secant squared u du. So this gives me 2 times the integral of secant cubed u du. One little typo. If you want to write those limits like I did, since you changed their letters to u, if you want to write the limits, you should say very clearly, theta is 0, not u. Theta is pi over 2. Now, this integral, we solved this by parts last semester in Calc 2. We got what's called the reduction formula. And it turns out that this integral of secant cubed u du is secant u times the tangent of u over 2 plus 1/2 times ln of secant u plus tan u. Ln of secant u plus tangent of u. Look up this formula. It's in some table in your book called the reduction formula. Okay, I can factor out the half and it'll kill off the 2 in the front. 2 times the half is 1. Secant of u, using my triangle up there, is just theta square root of theta squared plus 1 times tangent of u is theta. I'll put the theta first. Plus ln of the same things except we add them. Secant u is the square root of theta squared plus 1 plus theta plus tangent of u, which is theta. And again, we want to evaluate this, believe it or not, from 0 to pi over 2. And we're just ready to crank this out. You really shouldn't get it wrong from here. Wherever you see theta, first we plug in pi over 2. Boom. Theta, pi over 2. Theta, pi over 2. Pi over 2, square root of pi over 2 squared. That is pi squared over 4 plus 1 plus ln of the absolute value of the square root of theta squared, which is pi squared over 4 plus 1 plus pi over 2. Now, if we plug 0 in, that's going to be 0. And 0 times 1 is 0. And over here, we're going to have 0 plus, we're going to have 1 plus 0, which is 1. This mess will be 1. But ln of 1 is 0. So plugging in 0 doesn't give anything. Now, just want to clean this up a little bit. I'm going to think of this 1 as 4 over 4. So what I get is pi over 2 times the square root of pi squared plus 4 over 4 plus same thing in the ln. that square root will just be pi squared plus 4 over 4 plus pi over 2. When you have a fraction underneath the square root, you can take the square root of the top, which I don't know, so it's just the square root of pi squared plus 4, and you can divide that by the square root of the denominator. The square root of 4 is 2. Same thing under, by the ln, excuse me. The bottom, the square root of 4 is just 2. Now, 2 times 2 is 4. So you get pi, the square root of pi squared plus 4 over 4 plus, in addition, if the bottoms are the same, keep it. It's the ln of 2's in the bottom, which is positive, and the square root of pi squared plus 4 is positive, and then you add pi, you add more, it's positive. That is, you don't need the absolute value bars anymore. And there is your answer. There is the answer. And on that note, that finishes up this section. Thank you.